For our next standard in Chapter 5, we are going to be graphing and identifying characteristics of polynomial equations. In order to earn a level 1, you need to be able to take a graph that already has all the listed points and match it with the y-intercept, the relative minimums and maximums, and the zeros. Level 2 and 3 are just varying degrees of being able to graph a polynomial. In level 2, you would be able to identify and plot 3 of the characteristics listed. In level 3, you would be able to do all 4 of the characteristics listed. In level 4, we actually have to be able to take a graph and identify 4 new pieces of information. So each of the problems that we're going to work through, we are going to work on all of the skills for levels 1 through 4, kind of all together here. But there's some pieces of information that you don't know yet or you haven't heard yet, even though a lot of the information will repeat from quadratics in Chapter 4. The first thing that I want to discuss is odd and even degree functions. A degree is the highest exponent of a polynomial. And so when something is odd degree, the highest exponent is an odd number. When something is an even degree, the highest exponent is an even number. Odd degree functions always have an odd number of real zeros, and they also share some characteristics in other ways too that we'll talk about later. Same with even degree functions, they share characteristics as well. Even degree functions always have an even number of real zeros, or they could have no zeros at all. We saw that when we had parabolas that were hanging above the x-axis. Those had no zeros at all. They had only imaginary answers. When we are talking about end behavior, I want you to always think of and write down immediately what's written in black there. I guess it's all written in black. What's written in bold here. As x approaches positive infinity, f of x approaches blank. Same for as x approaches negative infinity, f of x approaches blank. I put it in words here how you would read that because we don't often know what the arrows translate to. But these two things specifically, every time it asks for end behavior, you will write both of these two things before you even look at the problem, because the end part will be just identifying whether I put positive or negative infinity in here, depending on what the end of the graph is doing. We're going to practice end behavior several times on the next page. You may want to pause the video here and make sure that for each of these you have written down that skeleton of an answer for end behavior. The as x approaches positive infinity, f of x approaches, and same for negative infinity for linear, quadratic, cubic, quartic, and quintic functions. Now that we've had a chance to write that down for each one, we can focus on just filling in the blanks for each of these. Now we know what the degree is because it's said it right at the beginning. So degree of 1, degree of 3, and degree of 5 are all odd degree functions. And you should see some characteristics that the end behavior will share for those. Degree 4 and degree 2 are both even degree functions, and they'll show characteristics with their end behavior as well. When we're looking at end behavior, whenever it has as x approaches positive infinity, we are always looking at the right arrow, the right end of the graph. And the right end of the graph here is pointing up. So therefore, we will say that f of x, which is a fancy way of saying y, is approaching positive infinity. When x approaches negative infinity, that will be the left arrow or the left end of the graph, and it's pointing down. So we would indicate that f of x is approaching negative infinity. So whenever the arrow is pointing up, we'll say f of x approaches positive infinity. When the arrow is pointing down, we'll say that f of x is approaching negative infinity. Let's do the quadratic. So the right arrow is x approaching positive infinity, and that right arrow is pointing down. So we will say f of x is approaching negative infinity. The left arrow for x approaching negative infinity is also pointing down, so we will also indicate negative infinity for f of x. For our cubic functions, the right arrow for x is positive infinity is pointing up, so we will put positive infinity for our f of x, and the left arrow is pointing down, so f of x will be approaching negative infinity. For our quartic function, x approaching positive infinity is our right arrow. It's pointing up, so it will also approach positive infinity for f of x. As x approaches negative infinity is our left arrow. It's also pointing up, so it's positive infinity. For our quintic function, our right arrow for x approaching positive infinity is pointing up, so we will say positive infinity, and our left arrow is pointing down, so we will say negative infinity. You may have noticed that with the odd degree functions, each time we had one of them was negative infinity and one of them was positive infinity. They will always have f of x approaching opposite sets of infinity when it's an odd degree function. We can look at any graph, even if they didn't tell us the degree, and be able to indicate whether it was an odd or even degree based off its end behavior. If the ends are pointing in opposite directions, it's an odd degree function. Same kind of thing can be told with an even degree function. Our end behaviors were the exact same for our even degrees. When x approaches positive infinity and negative infinity, f of x approach the same for both. So even degree functions, we can tell the graph by looking at the ends. If they're pointing in the same direction, we will identify them as an even degree. Moving on past end behavior, I want to discuss the number of real zeros. Now, the number of real zeros would be the number of times that it crosses the x-axis. So, for example, we had crosses once. Here it crosses twice. And we said on the other page that odd degree functions have an odd number of real zeros, and even degree functions have an even number of real zeros or no zeros at all. But they also are a good indicator to tell me what's the smallest degree for that function. If I have something with 4 real zeros, then the smallest degree that that function can represent is something with a degree of 4. The number of zeros can never be bigger than the minimum degree. So the number of zeros can never be bigger than the degree. So 3 real zeros, the smallest degree would be 3. 5 real zeros, the smallest degree would be 5. Now I said smallest degree. So since there were 5 real zeros here, I could have had a function with 5 real zeros that had a degree of 7 or a degree of 9, because those are odd numbers that are bigger than the number of real zeros. Let's talk about turning points and relative minimums and relative maximums. Turning points are just another word for a maximum or a minimum value in a function. And if I have a polynomial, I can count the number of turning points and find out what's the minimum degree from that as well. Because the number of turning points, the most number of turning points, would be the degree minus 1. So for example, if I had been given that the degree is 6, 1 less than that would be 5, that would help me see that there would be at most 5 different turning points, or 5 different hills and valleys, maximums, minimums, whatever you want to call them, on that graph. Quadratic functions have a degree of 2. So the maximum number of turning points in a quadratic is 1. That's why they all look the same and looked like a parabola. You'll see with cubic functions, especially later, because those are the ones that we deal the most with in this chapter, that they will have either one turning point or no, well, I guess they'll have to have two turning points or one turning point. We can't ever have more than two turning points though. Let's actually put all this information together and look at what a level 1 type problem would look like. Now technically this is more like a level 1 / level 4, meaning this would be level 1 type material up here as well as the end behavior. Oops, sorry, I said that in reverse. This and end behavior would be part of a level 4 problem, and the relative max min, zeros, and y-intercept would be more part of a level 1 problem. But both of them would be given a graph. Can you tell information about it? So given a graph, can I tell whether this is odd or even? This is an odd degree function because the ends point in opposite directions and the number of real zeros is odd. So it is an odd degree function. There are 3 real zeros in this function, which means that the smallest degree or the minimum degree is also 3. We're going to jump down and do the end behavior really quickly. Now they've already had the skeleton answer here for you, so all you have to do is fill in negative and positive infinity. So the right arrow would be the first one. It's pointing up, so positive infinity. The left arrow is pointing down, so we would say negative infinity. For the other pieces, we just have to match each of the given points with what the name for that part would be. So the relative max, we say relative maximums and relative minimums when we're talking about polynomials, because sometimes that are the maximum value for the function, and sometimes they're just the highest point relative to the points on either side of it. Like for example here, I don't have an absolute maximum because this goes up forever. This end goes up forever. There isn't a highest point. But I do have a relative maximum because this hill is higher than points on either side of that point. So our relative maximum would be negative 2.18, comma 4.01. Our relative minimum would be down in the valley at 1.28 and negative 5.21. The zeros would be right along that x-axis. Make sure that you're writing them as points. And the y-intercept right along that y-axis is at 0, negative 2. Now let's actually take a shot at graphing these. To graph these, you're going to need your graphing calculator. We are going to go to y equals, and type in our equation into y equals after we've cleared out anything that might have been there. It's always a good idea to hit zoom and 6 the first time that you sit down to graph to make sure your window is set at a standard window. And here we have our graph. We can tell just by looking at it a couple of things. We can tell that it is an odd degree because the ends point in opposite directions. We can also tell how many real zeros there are. 1, 2, 3 real zeros. Because there are 3 real zeros, We are also able to tell the minimum degree, which is also 3. We need to be able to write our end behavior. So as x approaches positive infinity, f of x approaches. As x approaches negative infinity, f of x approaches. So positive infinity would be the right side. It's pointing up, so it will also be positive infinity. Negative infinity would be the left side. It's pointing down, so it would be negative infinity. Now that we've labeled those pieces, we are going to find all the zeros. We're going to find the relative minimums and the relative maximums. And finally, we'll find the y-intercept. So for the zeros, I don't want you to use the trace tool because it may look like you're getting the zeros. It looks like it's close. It looks like it's at the 0, but it's actually not. It's a little off. We want to actually make the calculator calculate. So second calc, 0. We're going to move our cursor to the left 0. That's the one I'm going to focus on first, and we'll move across. So the left 0 means the left bound would be in the down end of the graph. So we'll press enter. The right bound would be somewhere on this hill, and we'll press enter until it pops up with 0 and the number. So we have negative 2.77, comma, and we get this weird E thing, which is just scientific notation. It's point and then 11 zeros and then a 1. So I think we can safely assume that that's really at 0. So whenever we see this E, we assume that it's 0. Second calc, option 2. We're going to do this process 2 more times to find all 3 zeros. So for the middle one, the left side would be somewhere on the hill. The right side would be somewhere in the valley. And press enter until we get our 0. Negative 0.48, comma 0, 2 decimal places. Repeat the process. Second calc, option 2. Left side would be somewhere in the valley this time, and the right side would be somewhere on our end that's pointing up. And press enter until it tells me the 0 at 2.25, comma 0. And there's that weird E again. Now it's time to find the maximum and the minimum. I know I only have one because I have one hill, and I only have one minimum because I only have one valley. So second calc, maximum, that's number 4. Go to your hill. We're finding the left side of the hill. Press enter. The right side of our hill, and press enter until it says maximum and spits out the number. Negative 1.79, comma 5.21. Let's do it again for the valley this time, the minimum. Second calc, minimum. Left side, we're on the left side of our valley. The right side, we're on the right side of our valley. And we press enter until we have a minimum at 1.12 and comma negative 7.06. Now we're going to do the y-intercept. 2 ways that you can find the y-intercept. One way is to look for the term that doesn't have a variable, negative 3. So our y-intercept would be 0, comma negative 3. The second way is to press second and graph and find where x is 0, because that would be your y-intercept, 0, negative 3. We are going to plot these bottom 4 things on our graph, and that's what will make up our paper version of the graph. So we'll plot each of our zeros, negative 2.770, negative 4 negative 0.48, and then positive 2.25. Just do your best to estimate them. Relative maximum at negative 1.79, 5.21. And our minimum, our relative minimum at 1.12 and negative 7.06. Now how I like to make my graph is I connect my hills and then I connect my valleys before drawing my ends. So there's my hill. Here's my valley. That way I can make sure that it is curved like it's supposed to be. And then I go back and draw my ends. Find I have a lot more control over the shape that way. We've got 3 more examples to work through. So I'm going to start by putting number 2 into my calculator for y equals. There it is. It's into my calculator. We'll go ahead and just hit graph this time because I didn't change my window last time. So there's no need to press zoom 6 this time. Same kind of shape of the graph as what we had previously. The ends are pointing in opposite directions, which tells me that it is an odd degree. Again, if they were pointing in the same direction, it would be an even degree. There are 3 total real zeros, 3 places that cross the x-axis. And that means that we have a minimum degree for this of 3. And we can write in our beginnings of our end behavior. There's the beginnings of our end behavior. Looking at the graph, the right arrow is pointing up. So I'll use positive infinity to represent what f of x is doing. The left arrow is pointing down, so I'll use negative infinity to represent what f of x is doing. To find the points that we'll need to plot, we will use our zeros, our relative minimums, and our relative maximums. And finally, our y-intercept. To find our zeros, we'll press second, and then calc, 0. Again, I like to start on the left, so this time the left side would be the end that's pointing down. The right side would be the hill, and press enter until I get my answer, which is at negative 0.640. We're going to repeat this process 2 more times. Second calc, option 2. Left side this time would be part of the hill. Right side would be part of the valley. And we have a 0 this time at 0.48, 0. And one more time to find the last 0. Second calc, option 2. This time the left side is in the valley. The right side is in the right end of the graph. We have 2.17, 0. Now that you have located all 3 zeros, we're going to find any relative minimums or relative maximums. So for relative maximums, that would be any hills. There is one hill. So second calc, maximum. We'll move our cursor to the left side of the hill. Then follow along and move our cursor to the right side of the hill. And press enter until it says maximum and gives us the number. The maximum is at negative 0.15, comma 2.15. It's the same process, but this time we'll select minimum and we'll use the valley. So minimum, left side of the valley, right side of the valley. And we get that our minimum value, our relative minimum value, is at 1.48, comma negative 4.38. So 2 decimal places. Find your y-intercept by either using the table and finding where x is 0, or by finding the term that doesn't have an x. Either way, 0, 2 is my y-intercept. We're going to go ahead and plot all of these points. Remember, this top part is just that information. The bottom 4 lines are what we're going to actually plot. Negative 0.64, positive 0.48. I know that they're really close together, and if you wanted to count by halves, you absolutely could. Just make sure that you label your graph whenever you count by anything other than 1. And then 2.17 over here. Let's follow the same process for our relative minimums and maximums. We'll connect our hills, just a very skinny hill here. Connect our valley. Then we can go through and draw our ends. We'll do this 2 more times. This time, our leading term, or our leading coefficient, is negative, which is going to do something a little different for our end behavior. Just typing it into my y equals. Graph. I can see on my graph it's a similar shape to what we had, except for it's going up over here on the left side, but it's still an odd degree function. It still has 3 real zeros. Which means its minimum degree is 3. Let's write in our skeleton of our end behavior. So as x approaches positive infinity, that's our right arrow. And this time our right arrow is pointing down. So we will say that it is f of x is approaching negative infinity. As x approaches negative infinity, that's our left arrow, and it's pointing up. So we will say that f of x is approaching positive infinity. We have 3 real zeros, so let's work to find them. We also have 1 relative maximum. a relative minimum, and we have a y-intercept. So for our zeros, we'll press second calc, option 2, left side of the 0, right side of the 0. So I used the upper N and the part of the valley, and I got my 0 at negative 0.3, comma 0. We're going to repeat that process. Second calc 0, we're going to find that minimum. So the left side is in the valley, the right side is in the hill, and we get a 0 directly at 1. Second calc 0, left side is in the hill this time, right side is in the right hand end, the right end, and we have a 0 at 3.30. Let's repeat this process, but this time selecting maximum. So we're trying to find the hill, so we'll move the left side of the hill, the right side of the hill, and we get 2.39, comma 3.42. And for our minimum, second calc minimum, we'll need to find the valley. So left side of the valley, right side of the valley, and I get the minimum is at 0.28, comma negative 1.27. Our y-intercept, either the term that doesn't have a variable or from your table, we get 0, negative 1. And we're going to plot those points now. Oh, my 3.3 looks like a 3, comma 3. For my 0, our maximums are at 2.39 and 3.42, and our minimum 0.28 and negative 1.27. Our y-intercept is at 0 and negative 1. I know they're really, really close together. You're just going to do the best you can to connect them. This is just a rough sketch of our graph. Obviously, we have some limitations here in getting as close as possible. This one would be a great example. Oh, I did graph the minimum on the wrong side too, but this one would be a great example of one that would be very helpful to spread out that scale so that you're not counting so close to each other. I plotted my max or my minimum value at negative 0.28. It should have been at positive 0.28. Last one, and the last one holds a little bit of a surprise for us. I'm going to type it into my y equals. Here we go. And we can see that it doesn't look like our other 3 graphs that we've plotted. It still has the similar end behavior. So ends are pointing in opposite directions. That still makes it an odd degree. It has 1 real 0. Which means the minimum degree is 1. End behavior, writing in that skeleton of an answer. The right arrow is pointing down, so we'll use negative infinity to represent what f of x is doing. The left arrow, or left side, isn't going up, so we'll use positive infinity to represent what f of x, or y, is doing. And we'll need to find the only zero that's there, but there is no minimum and there's no maximum. So you can put relative max and relative min. We'll just say there's none. Let's go ahead and find that zero. So second calc, 0. Left side of the 0. Right side of the 0. And we have 1.65. And our y-intercept is 0, 4, or from your table, 0, 4. So I have 1.650 and 0, 1, 2, 3, 4. That is not enough, in my opinion, to get a good shape for this graph. So if you use your table, remember we got there by pressing second and table, you can find a few other points that would fit that might be a good way to show the better shape on here. So for example, negative 2, 26, that's not going to fit, but negative 1 and 10 will fit. We could also get a point at 1 and 2. And 3, negative 14 is not quite going to fit. But we know that it would be down slightly off the graph. Connecting these points will at least give me a shape of my graph.